Hello everyone. Today we are here to explain about assignment SEM 2 to 2024 and 2025. We are from Faculty Technology and Computer Electric. Our subject is BELK 1333 Advanced Electric Circuit. First of all, I would like to introduce myself. I am Krishnapriya Napapatiru.
Assalamualaikum and hi. My name is Aminah Khoridiah binti Norman.
Assalamualaikum. My name is Alia Salsabila binti Nurhidan.
Hi, my name is Nur Azmina Alia binti Muhammad Sam.
Short introduction about Advanced Electric Circuit. It is about a transfer function. The transfer function is a mathematical expression that describes how the input of a circuit responds into its input in a frequency domain. It is defined as the ratio of the Laplace transform of the output to the Laplace transform of the input, assuming zero initial condition. This function helps engineers to analyze a circuit's behavior in terms of stability, gain phase shift, and frequency response. For example, in a RC low-pass filter, a transfer function shows how the circuit adheres high-frequency signal while allowing a low frequency to the pass. For my understanding, a transfer function comes from raw data, and in order to create a blood plot, we need to convert it into a standard form. This standard form makes it easier to plot and analyze the system frequency response.
Based on question B, to solve the question, we use conjugate multiplication to cancel out the term that doesn't justify or relate to the formula of transfer function. So first j omega plus 10 need to be multiplied with 10 over 10 for the numerator of the equation given. For the denominator, j omega plus 5 power of 2 need to be multiplied with 5 over 5 to cancel the 5. After that, we will get the answer as has been shown. For the denominator, j omega over 5 plus 1 power of 2 need to be solved, so we will gain 55 as the answer. Then for 10 at the numerator and 25 at the denominator, it need to be divided with 5. So we will gain the answer of 2 bracket of j omega over 10 plus 1, close the bracket, and for the denominator, we will gain the answer of 5 bracket of j omega and bracket of j omega over 5 plus 1. So that's all the answer for the transfer function.
This is the graph for the block plot from our transfer function. Okay, to draw this block plot, we have 2 over 5 as a gain for the block plot. So to start 2 over 5, we need to use formula 20 log 2 over 5 as a gain for this graph. 20 log 2 over 5, we will get negative 8. So we need to draw a straight line over negative 8 dB. So this is the line. Next, we have j omega over 10 plus 1, which is a simple zero, this one. Okay, so we need to start from a 0 because it's a simple 0, and then draw a straight line across 0 until it reach 10. And then draw a slope 20 dB over decade until it 1 decade after 10 radian second. So which is 100 over j omega. Okay, 1 over j omega is a pole at origin. So we draw pole at origin, which is here. We need to draw a straight line at negative 20 dB over decade. Okay, so don't forget to make sure the line cross the one here because it's a 1 over j omega. So this is the line for pole at origin. Okay, and then we have j omega over 5 plus 1, which is a simple pole. Okay, why it is a simple pole? Because it's the one that below. See, it's the same as 1 over j omega over 5 plus 1. Okay, so to draw a simple pole, which is this one. Okay, so same as simple 0, we need to start from 0 here. And then go straight until it reach 5 radian per second. And then make a slope at negative 20 dB over decade until it reach 1 decade after 5, which is 15. For critical point, we need to plot the graph at 0, 0.1, 1, 5, 10, and 15. Okay, to start it, we're going to start with at 0.1. So 0.1, we have the line that cross with 0.1, 20, and negative 8. So multiply these two and we will get 12. So we need to plot here 12 and then move to 1 radian per second. So for 1 radian per second, so we have 0 here, so 0, and then we have negative 8 here that cross with 1 here. Okay, so and we will get negative 8. So plot at negative 8. And then we have for 5 radian per second, for 5 radian, here negative 8 and negative 14 here. So multiply these two numbers and we will get, subtract these two numbers and we will get negative 22, which is we're going to plot here, negative 22. Okay, then at 10 radian per second, we have 0 here, and then we have negative 6 here, and then we have negative 8 here, and multiply this number and we will get negative 34. So plot here, negative 34. Okay, and then the last one, for 50 radian per second, okay, we have 0 here, 13 here, negative 20, and negative 34. And we will get negative 36. So we're going to plot here, negative 36, and connect all this plot and we will get a critical point for this graph.
Let me explain about question H. Before that, I would like to tell about this graph. It's a broad magnitude plot in the deliverable for transfer function A omega. The magnitude is flat. It's a flat dB up to omega 100 radians per second. After that, the plot dropped at the slope negative 20 dB per decade until omega 1000 radians per second. And then it is flattened again. You have to find out the initial magnitude level to find the constant K. So to find gain constant K, we have to use calculation of 20 log K. Our 20 log K is 40. So we have to divide it into 10 bracket 40 over 20. So the constant K gain value is 100. After that, second one, we have to identify the pole based on where the slope changes. First one is a simple pole at a slope negative 20 dB per decade at omega 100 radians per second. We will use 1 over 1 plus j omega over 100. After that, for the second one, we have to find j omega 1000 radians per second. That the slope level is off again. That means we have to add a simple zero with slope at positive 20 dB over decade at omega 1000 radians per second. So we will use the formula is 1 plus j omega over 1000.
I will continue for question H. Transfer function. We want to transform the transfer function into complex frequency. So first of all, we know that the gain of this question H from the dot plot is 100, and a simple zero is at omega 1000 radian per second, and a simple pole at omega 100 radian per second. So we rearrange the numbers like this question. 100 multiply with 1 plus j omega over 1000 and over 1 plus j omega over 100. So next, we want to eliminate the denominators and denominators for both fractions. So we multiply the 1 plus j omega over 1000 with 1000 over 1000. And also same goes with 100. 1 plus j omega over 100 multiply with 100 over 100. So when we multiply both of it, it will become like this equation. 1000 plus j omega multiply with 1 over 1000. And also same with 100. 100 plus j omega multiply with 1 over 100. So this 100 and 1 over 1000, we multiply both of it. So we will got 1 over 10. So we keep over 100. So the equation will be like this. So after that, 1 over 10 divide with 1 over 100. So we will got 10. So we want to transfer this equation to complex frequency, which is S. So the last equation will be like this. 10 multiplied with 1000 plus S over 100 plus S.
For the discussion, based on the question for both P and H, it can be clarified that to solve the question for transfer function, we need to use conjugate multiplication to get the right answer. That will be similar to the table of factor, gain, and phase as per in the note of the lecture. For the dot plot, the answer need to be referred to the table of transfer function that has been given by the lecturer and need to use 1 decade per each of the answer. And lastly, for the critical point, it needs to be referred to the last answer that we have been obtained for the transfer function equation. For equation H, from the dot plot, we need to change it to transfer function equation.
The conclusion of our discussion for these two questions is dot plot is a useful tool to understand how a system behaves in the frequency domain. To create a dot plot from a transfer function, we write it in a standard form to identify gains, poles, and zeros. Then we sketch the magnitude and phase plots by analyzing how each part affects the slope and angle at different frequencies. This helps in visualizing stability and performance. Conversely, we can estimate a system's transfer function from a dot plot by observing the slopes and corner frequencies, which reveal the number and location of poles and zeros. This two-way process is essential in control system analysis and design. So that's all from us. So thank you very much.